Hi, I'm Tuukka Korhonen, and I will talk about our paper, An Improved Parameterized Algorithm for Treewidth, that is joint work with Daniel Lokshtanov. So Treewidth is a graph parameter that measures how close a graph is to a tree. For example, trees have treewidth 1. This example graph here has treewidth 2, so it's quite close to a tree. The n times n grid has treewidth n. And the complete graph on n vertices has treewidth n-1. So treewidth is defined as the minimum width of a tree decomposition of the graph. So here is a tree decomposition of this example graph. So what is a tree decomposition? A tree decomposition is a tree of backs. So backs are subsets of vertices that satisfies some properties. So first, every vertex of the graph must be in some back. So this vertex A is in this back here. Then every edge of the graph must be in some back. So this, which means that both endpoints of the edge are in the back. So this edge between A and B is in this back because both A and B are in it. And then for every vertex, the backs containing that vertex must form a connected subtree. So for example, if you look at the vertex I, then it's in this back, this back, this back, this back, and this back. So they form a connected subtree of this tree. And the width of a tree decomposition is the maximum back size minus 1. So here the back size is 3, so the width is 2. So this tree decomposition witnesses that the tree width of this example graph is at most 2, and we know that it's exactly 2 because only forests have tree width 1. And tree width, this definition of tree width was given by Robertson and Seymour in their graph minor series, but equivalent definitions of equivalent parameters were given also independently by Arnold and Proskowski, and Pertile and Priosi and Hallin. Okay. So why treewidth? Well, a lot of algorithms that you can do on trees generalize to algorithms that works on graphs of small treewidth. So for example, when given a graph together with the tree decomposition of width k, we can solve a maximum independent set in time to the k times n, minimum dominating set in time 3 to k times n, Hamiltonian cycle in time like 2 to the O of k times n, and like any problem in this MSO logic in time f of k times n, or f of k is some function depending only on the width of the given decomposition. And what is the motivation of computing tree width and the tree decomposition giving the minimum width is that all of these results, they need this tree decomposition as an input. Yeah. And so this is what our work is about. Okay. So let's first review the literature and our result about computing treewidth exactly. And on the next slide, I will talk about computing treewidth approximately. Yeah. So computing treewidth exactly, it's known to be NP complete. Korhonen and Proskowski in 1987 proved that it's NP complete. And same paper, they showed that it can be done in time of n to the k plus 2, where n is the number of vertices and k is the treewidth. But this is not an FPT algorithm. So here, this poly n, the degree of the polynomial depends on k, but we want like f of k times poly n, which is like FPT. And this type of algorithm was given by Robertson and Seymour in the graph minor series, so f of k times n square, non-uniform algorithm. So this uses some black box results about graph minors. Yeah, so it's like we at the time of this result, they didn't know how to even construct this algorithm. Yeah, but anyway, this was improved, which culminated in Borlander's algorithm, given actually exactly 30 years ago at STOC 93, that computes treewidth exactly and the corresponding tree decomposition in time 2 to the O of k cubed times n. Okay, and how this algorithm works? Well, it's based on a dynamic programming algorithm of Borlander clocks and Lagerheim and Arnborg. So this was like given in ICALP 91 independently of each other. So they showed that if I give you a near optimal tree decomposition, then you can use dynamic programming on the near optimal decomposition to compute an optimal tree decomposition in time like 2 to the O of k cube times linear in n. And like repeating this n times, you can like add one vertex at a time and always compute the optimal tree decomposition. So you get like exact tree width in then like this times n square. And then this Portlander 93 was optimizing this to be like linear in n. Yeah, so this is like how this works is uses dynamic programming on Treewidth to compute Treewidth. And yeah, after this, like this is this dependence on n, it's linear, so it's of course it's optimal. But this dependence on k, we can ask, is this optimal? Can the dependence to the O of k cube on k be improved? This was asked first by Downey and Fellows in their monograph in 99. And yeah, and basically nothing happened before this work. So what we show in this work is that there is 2 to the O of k square times n to the 4 time algorithm for computing Treewidth exactly. And this is like a first FPT algorithm where this dependence on k is better than this 2 to the O of k cube given in 91 by Borlander, Lokshtanov, and Arborg. Yeah, but of course we have a cost of very high dependence on n. Yeah, and an interesting thing about our algorithm is that it doesn't use any dynamic programming. So these previous algorithms, like this, is very explicitly dynamic programming, and this is like minor testing that is like dynamic programming under the hood. But this our algorithm, it doesn't use any dynamic programming, so it runs in polynomial space actually, and it uses very different techniques than the previous algorithms. So this can be seen as a completely new proof that exact computing of Treewidth is FPT, parameterized by Treewidth. Okay. Yeah, so then we have also some results about approximating Treewidth. So let's first review the literature. So for polynomial time approximation, the best algorithm is O of square root of log k approximation given by Fage, Hayek, and Lee in 2008. And it's known that assuming this small set expansion conjecture, it's NP hard to constantly approximate Treewidth for any constant, which was proven by Wu, Austrian, Pitassi, and Liu in 2014. But if you look for FPT approximation, then of course we can get constant approximation because we can get even exact algorithm, but we can get constant approximation faster than exact algorithms. So already in graph miners of Roberts and Seymour, they gave a 4 approximation in time to the O of k times n square. So remember the exact algorithms, our new exact result was like to the O of k square, and the old was like to the O of k cube. So this is already much better dependence on k with some cost on approximation. And this was like this dependence on n in approximation, in FPT approximation was then in the beginning of 90s improved by Matosek and Thomas and Lagerheim and Reed to like n log square n and n log n. And yeah, then there was this 93 Borlander linear time algorithm. But then in 2016, the best of both worlds was achieved. So this to the O of k, so single exponential in k and linear in n approximation algorithm for Treewidth, so far approximation was given by Borlander, Rangetegi, Fomin, Lokshtanov, and Pilipchuk. And in 21, I improved this to be 2 approximation with different techniques. Also, this O of k was improved. And what we do in this work with Daniel, we have some FPT approximation for Treewidth, but this time we can go below 2 approximations. So we can do 1 plus epsilon approximation for Treewidth in time k to the O of k divided by epsilon times n to the 4. So again, very high polynomial. So our focus is on improving this dependence on k and this approximation ratio. So for example, if you set epsilon to be like 0.1, we get like 1.1 approximation for Treewidth in time k to the O of k. And how this compares to these previous results? Well, of course, already for true approximation like epsilon equals 1, this is much worse than this. But the novel thing is that we can do below true approximation faster than exact. So previously there was nothing below true approximation was nothing known that was better than the exact algorithms. But now we can, for any constant, we have k to the O of k that is faster than like this 2 to the k square exact. And this epsilon, it's an arbitrary input. So you can set epsilon here to be like 1 over k. So you get actually an exact algorithm of this, which is like k to the O of k square. So this is like, it's almost as good as our exact algorithm from the previous slide. So it's like only like log k in the exponent difference. So this gives like already this approximation scheme improves over the previous exact algorithms on the dependence of k on k. And and our like this exact algorithm can be thought of as just optimization of this in the setting when you set epsilon to be equal to like 1 over k. Okay, then let's go to more details about our algorithms. So I'll give an overview of both of these algorithms. Like they follow both the same plan and the same basic techniques. The differences are only in some very much details that I don't have time to go in this talk. Yeah, so the overall strategy is to iteratively improve a tree decomposition. I'll later say in what sense improve, but the point is to apply some improvement operation to tree decompositions multiple times to iteratively make it better. Okay, so our first part of our result is to show how to improve a tree decomposition. And what we show is that to improve a tree decomposition, it's sufficient to solve a problem we call the subset Treewidth problem. So this subset Treewidth problem, it's a new problem that we introduce just for the sake of this result. And we show that, and we give a reduction that shows that if you give an algorithm that solves the subset Treewidth problem, then you can apply this algorithm a polynomial number of times to actually like compute exact Treewidth. Or like if I give you an approximation algorithm for subset Treewidth, then you get also approximation algorithm for Treewidth with the same ratio. And again, with just polynomial number of applications of the algorithm. Okay, so this is our first theorem, is to show this connection between subset Treewidth and Treewidth. And the techniques for this is basically a generalization of this tree decomposition improvement method from my 2 approximation algorithm from 21. So there we could improve tree decomposition up until 2 approximation, but with this subset Treewidth problem, we actually can improve it until like it's exactly the Treewidth is the width of decomposition. And here the techniques inside is like there's this what we call pulling argument of like pulling separators along disjunct paths inside the decomposition to rearrange this tree decomposition. And this type of arguments, so this originates from proofs about existence of lean tree decompositions of Thomas and Belenbaum-Diestel, and this was used in this 2 approximation, and now we make use of it more in the context of this subset Treewidth problem. And then the second part of our proof is, of course, actually solving this subset Treewidth problem. So we give algorithms, so we give an exact algorithm and an approximation algorithm for the subset Treewidth problem that then combined with this first theorem actually give our main results, this exact algorithm and approximation algorithm. And here, the techniques of this is we have the main engine basically is branching on important separators. So these are like separators of size k that are in some sense maximally pushed towards some vertex set in a graph and like bounce on this. This machinery was introduced by Marx in 2006. So we make a lot of use of this. And inside there, like for arguing why we can actually do this is again this pulling application of this pulling argument of rearranging tree decompositions, but at this time in the context of actually this tree decomposition for this subset Treewidth instead of the normal Treewidth. Yeah, so this is the overview. Okay, so then the rest of the talk I will use to explain this first part of our work. So this subset Treewidth problem and how we use this, how this subset Treewidth problem can be used for improving a tree decomposition. So let's start with how exactly are we improving the tree decomposition here? So the setting is that we have some tree decomposition T, whose largest back is W, and we wish to improve this tree decomposition T. So what's our goal is either to decrease the number of backs of this maximum size. So this W was the largest back, so we want to decrease the backs of size this W while not increasing the width of the decomposition, or to conclude that this decomposition is optimal or approximately optimal. Okay, so what happens is that if we go to this, of course, if we go to the second case and conclude that we have optimal tree decomposition, we are happy. And then if we do this, repeat this first thing, so we are decreasing the number of largest backs while not increasing the width. We start with like at most n largest backs. So after n iterations of decreasing this number of largest backs, we actually must improve the width of the decomposition. So that is somehow the point. So we can repeat this for the Treewidth of Treewidth times n iterations, this iteration to get an approximately optimal tree decomposition or optimal tree decomposition. And here we can assume to start with constant factor approximate decomposition by either using Borlander compression or by starting with like two approximation algorithm. Yeah, so this is now our setting. We have this, we fix this large back W and root this decomposition on this large back W, and now we wish somehow to get rid of this large back. Okay, so what we do, we have this large back W of this decomposition, and what we want to improve this decomposition, what we want to do, we want to find a set of vertices X that is a superset of this large back, and a tree decomposition of a graph called torso X of width at most the size of W minus 2. So what is this size of W minus 2? Well, because it's smaller than the width of this decomposition T that we have. Like the width of this is like W minus 1. So what we want to have is width W minus 2. So a better width than what we started. Okay, but what is this torso X? Okay, so this will be the subset Treewidth problem. So what is this torso X? So if we have some set of vertices X in the graph, that is here we want it to be superset of W, then this torso means we look at this set X in the graph and we look at the components of G minus X and we make their neighborhoods into a cliques. So here like this is a component, 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 and for each of these, this green thing here represents like their neighborhood made of a clique. So we made the neighborhood and clique, and then delete everybody outside of X. So this graph is the torso X. So it's like it's like the subgraph of X, but it gets some connectivity outside of X. Like it gets all the possible connectivity outside of X. So this is so we want to find this set X and the tree decomposition of this torso X that is better than our tree decomposition T. Okay, so this is the subset Treewidth problem. Let's start with some observations. So if you look at let's say our W, the back we want to improve, it looks maybe like this in the graph for some reason. I don't know. There's 4 vertices. First observation, if our tree composition T that we have is not optimal, then this kind of set X always exists by just taking X equals to all of the vertices of G, because then the torso X is just the same as G, and we can have the tree composition of torso X to be just like the optimal tree composition of X. So we know that for non-optimal, when this W is large bag of non-optimal decomposition, then the solution of subset Treewidth always exists. But of course, this solution is somehow very trivial. It doesn't give us any insight. But what is the crucial thing here is that here we have freedom to choose this X. So we have freedom to throw something out of X, maybe look like this. So we take only these green areas to the X and take like only the composition of them. And this turns out for some reason to be very helpful in computing Treewidth. Okay. And there is alternative formulation is that a big leaf formulation is that we want to find a tree composition of the whole graph G so that the internal backs of the tree composition have size at most this. So the internal backs have width at most this. And this set W is contained in the internal backs, but the leaf backs can be arbitrarily large. So this is a big leaf formulation of this subset Treewidth problem. Okay. And now how we use this to improve our decomposition T. So here is our decomposition T. What we do basically, we have this, say we have this set X as a green here, and then we have some components of G minus X, this C1, C2, C3. And how we rearrange this decomposition when given this set X and a tree decomposition TX of this graph torso X, what we do, we just put this TX, so this TX is now like very much improved. So this has, well, backs are smaller than this W. So we basically kind of like replace this W by this TX. And then we look at these components. And these components, basically their neighborhoods are clicks in this torso X. So there is like backs that we know that we can somehow attach them. So we have like this neighborhood of C1. It lives in like one back here. So we attach kind of decomposition induced by this decomposition into here. And we have to do some surgery of actually pulling the neighborhood up. And this argument why this surgery of pulling the neighborhood up here is actually good, doesn't make the backs larger. This is the pulling argument. So this pulling argument shows that basically these decompositions that we attach here, even after this surgery, they are not worse. But this TX, this decomposition of torso X, it is better. And we somehow, like this, we got rid of this large back W. And now we got one large back less. So this is somehow the main intuition of this using this subset Treewidth for improving tree decompositions. Of course, there's you have to prove that this pulling argument, things like this work, but it's in the end it turns out to be working. So then what this results for exact algorithms, okay, we have this subset Treewidth formulation, we have this graph G, integer K, set of vertices of size K plus 2, and we want to find this superset X and a tree composition torso X of smaller width, or the concrete derivative of G is larger than K. And we show, so now this K is both like the size of this W and that like the target width of this decomposition of torso X. And what we show is what we show and what was sketched in the previous slide is that if there is f of k times Polygon algorithm for subset Treewidth, then there's f of k times Polygon algorithm for Treewidth with the same function f. And this is like actually if and only if because of some technicalities in the definition. And so what happens in the result is that this algorithm for subset Treewidth implies this algorithm for Treewidth. And then the same, almost same is for approximation schemes, but there we have like partitioned subset Treewidth. So there we have like this, so W is partitioned into T clicks W1 through WT. And this is the only difference. And then we show that basically an algorithm for partition subset Treewidth, where this 1 over epsilon goes to the number of clicks, goes to this t, gives an 1 plus epsilon approximation for Treewidth for the same function t. So actually, we don't give an approximation algorithm for subset Treewidth, but we give like algorithm for partitions for Treewidth, but it's like a proxy for approximation of subset Treewidth actually. But anyway, yeah. And what we show is that this k to the O of kt times poly n algorithm for partition subset Treewidth implies this time 1 plus epsilon approximation for Treewidth. And this is what happens in our result. Okay. So in conclusion, we have 2 to the O of k squared times n to the 4 time algorithm, and k to the O of k divided by epsilon times n to the 4 time 1 plus epsilon algorithm for Treewidth. And this is the first improvement on f of k in f of k times poly n Treewidth algorithms, since the algorithms of Borland and Lokshtanov and Lagerfeld and Arpanok in 91. And some interesting open questions in this area, of course. The question that we made the first progress in a long time is, what is the best f of k so that Treewidth can compute an f of k times poly n time? And in the lower bound regime, like the next problem here, I think that would be nice to show would be to give a 2 to the omega of k lower bound for this f of k, assuming ETH. Like the current reductions, they give a 2 to the omega of square root of k, and it's actually, this is we have a very wide gap. Like I would really believe that this lower bound would hold, but I have tried and I cannot show it to hold, at least currently. So yeah. So that's all. Thank you.